Hi everyone. So this week we're moving on to talk about space. The rest of the term will be concerned with space and time. We're starting by focusing on space, um, and in particular, a debate that has framed philosophical thinking about space from at least the time of Newton and Leibniz onwards. And that's the debate between so called absolutists about space and, on the other hand, relationalists about space. So, um, the absolutist about space, sometimes this view is called substantivalism, because the absolutist thinks of space as kind of like an independently existing substance. So specifically, they think that space exists independently of the objects located in space. So, um, kind of metaphorically speaking, figuratively speaking, space is like a container that contains objects. So a certain analogy might be given with something like a fish tank. So it's a container in which objects are placed, like fish and shells and water. Um, Now, that analogy has limitations because it might be that space is infinite in extent. Unlike a fish tank, it might not have boundaries. But nevertheless, the analogy holds to the extent that the container exists independently. The fish tank exists independently of the fish in it, and indeed you could have an empty fish tank, and the fish tank would still exist even if it were empty. So the substantivalist or the absolutist thinks that likewise space could exist even if there were no objects within it. And the notion of spatial relations, when it comes to spatial relations between objects, like distance relations, then the idea is basically two objects stand in a certain spatial relation, say distance relation, in virtue of just where they're located in absolute space. So, uh, say Big Ben would be located 300 miles from the Eiffel Tower, if and only if the region of absolute space that Big Ben occupies is 300 miles from the region of space that the Eiffel Tower occupies. We understand all those spatial relations in terms of location in absolute space. So the relationist contrasts with the absolutist or substantivalist in that they don't think that space has an independent reality over and above the spatial relations between objects within space. So they think that space wouldn't exist if there were no objects. So the notion of an empty space, a perfectly empty space, or in other words, a possible world where we have space but we don't have any objects, is an incoherent supposition. So all there are spatial relations and not an absolute space. So spatial relations like distance relations are taken as primitive or basic. They can't be analysed further. So it might just be a brute fact to not be explained any further that Big Ben is 300 miles from the Eiffel Tower. I'm probably completely off with what the distance is, but it was just an example. Okay, so that those are roughly the positions, and we'll sort of see what those positions look like in a bit more detail once we've got some arguments in play. So, one of the most famous arguments for absolutism is an argument given by Isaac Newton himself. So he thought that space was absolute, and specifically had a Euclidean geometry, and his laws of motion were framed in terms of an absolute space. So he thought he needed to provide some argument that space was absolute. So he gave an argument that's a famous argument known as the bucket argument. And basically it relies upon evidence of a particular experiment. So actually he thinks that a particular experiment can have a bearing on this metaphysical question of whether space is absolute or relational. So what I'm going to do is I'm going to run a video that illustrates, that exhibits the bucket experiment. And I'll run it, and then I'll explain to you what's going on with that experiment. So let's just watch the experiment. So this is obviously a version of it that I conducted at home, not using a bucket, but actually a bottle with some water in it, assisted by my French bulldog, George. So what I've done is I've taken the bottle, tied a bit of string around it, and then suspended it from the ceiling. And then what I do is I rotate the bucket so as to wind the string up before then releasing the bottle and seeing what happens. So I'll press play and we'll see what happens. Okay, so I'll play it a few more times just so you can watch as I explain what's going on. So I release the bottle. The bottle starts rotating because the string is wound up. And what's interesting is what happens to the shape of the surface of the water during this experiment. So what you'll observe is that when the experiment first begins, when I am about to release the bottle, then the surface of the water is flat. Now, as the water picks up speed under the frictional influence of the sides of the bottle, the surface of the water becomes increasingly concave. So dips in the middle, in other words. So flat surface, increasing concavity at this stage, and then at a certain point it becomes reaches maximal concavity, and then the bottle starts to slow and the surface of the water flattens out again. So those are the key observations from that experiment. Now, might surprise you, but Newton argues that this experiment shows that space-time is absolute. So what's he thinking? Well, let's recap just what's going on. So before I release the bottle, the water isn't moving relative to the sides of the bottle, right? So intuitively, both the bottle and the water are stationary before I release the bottle. So that's to put it in absolute terms, but we can put it in relational terms, just saying that the water isn't moving relative to the sides of the bottle. Stage 2, after I release the bottle, the water is moving relative to the sides of the bottle. Because the water isn't yet rotating as fast as the bottle. So the bottle picks up speed before the water does. It progressively imparts speed, accelerates the water due to the friction between the bottle sides and the water. So the water progressively picks up speed and catches up with the bottle. And so at a stage kind of in the middle of the experiment, before the bottle starts to slow down again, the bottle and the water are moving at the same speed, and that's when we observe the maximal concavity of the surface of the water. At this stage, they're moving at the same speed, and so they're not in relative motion. They're not moving relative to one another. Saying they were moving relative to one another would imply that one is moving differently from the other, but in this case, they're both moving in the same way, rotating at the same speed. Okay, so there's the sort of key observations of what's going on here, and you can check empirically that these observations are correct. So one way of checking that at the point at which the sort of midpoint of the experiment, when the bottle's moving fastest, that the water isn't moving relative to the bottle, is you can put a mark a dot on the side of the bottle, and also put a drop of ink into the water, and you'll find that there's no relative movement of those with respect to one another, at least if you perform the experiment well. Okay, so now what Newton points out is that there's a physically detectable difference between the first stage of the experiment, the stage at which just before I release the bottle, and what I've called the third stage of the experiment, the stage at which the water and the bottle are moving at the same speed, sort of midway through the experiment. And this physically detectable difference is the concavity of the water. So in the first stage, the water's perfectly flat, the surface of the water's perfectly flat. In the third stage, the surface of the water is concave. Now, so what Newton argues is we've got this empirical difference, but we can't explain this empirical difference in terms of the relative motion of the water in the bottle. And that's because at both the first stage and the third stage, the water in the bottle aren't moving relative to one another. There's no relative motion there. So in the first stage, if we were thinking in absolute terms, what we'd say is that neither the water nor the bottle is moving, and so they're not moving relative to one another either. They have the same motion. At the third stage, if we were speaking in absolutist terms, we'd like to say that they're both moving, but they're moving at the same speed. And yet we observe, so that again means they're not moving relative to one another. So even though at the first stage and the third stage, at neither of those stages is the water and the bottle moving relative to one another, nevertheless, there's this empirically detectable difference between the first and the third stage. So what Newton argues is that we can only explain this physical difference between stages 1 and 3, namely the flatness versus the concavity of the water, in terms of a difference in absolute motion between stages 1 and 3. So in stage 1 would say that the water and the bottle are not in absolute motion. At stage 3, we'd say that they're both in absolute motion. So provided we were allowed to appeal to absolute motion, we can explain the difference, the empirically observed difference, whereas Newton thinks we can't explain it in terms of relative motion because both stage 1 and stage 3, the water and the bottle are not in relative motion with respect to one another. There's a slight complication in that, strictly speaking, even at stage 1, the bottle and the water aren't at absolute rest. So we tend to think of them as being at rest. But after all, the Earth is rotating and orbiting the Sun. So strictly speaking, they're both in motion. However, what we do have is we have a difference in absolute motion, according to Newton, between the first stage and the third stage, even though we don't have a difference in relative motion. Now, actually, it's worth noting that it's not just that there's a difference in absolute motion between stage 1 and stage 3 in this experiment, but actually there's a difference in absolute acceleration between stage 1 and stage 3. That's quite important. We'll come back to this, because actually, strictly speaking, according to Newton, what explains the difference in the shape of the surface of the water isn't motion, but rather it's acceleration. So in stage 1, we'll set aside things like the spinning of the Earth and the orbiting of the Sun, just for simplicity. But in stage 1, we'd say ordinarily that the water and the bucket, neither of them are accelerating. Whereas in stage 3, they're both accelerating. Why are they accelerating? Well, acceleration is defined in terms of change in velocity. What's velocity? Well, velocity is actually different from speed. So hopefully we all know what speed is, at least roughly. So it's change in position. Speed is not a directed. So in the jargon, it's a scalar rather than a vector quantity. So you can move in the same speed in different directions, right? So you could be moving 30 miles per hour east to west, or 30 miles per hour west to east, same speed, different directions. Velocity differs in that it's what's known in the jargon as a vector quantity rather than a scalar quantity. So direction is critical. So it's defined not just in terms of a magnitude, a speed, but also in terms of a direction. So if you're moving 30 miles per hour east to west, and someone else is moving 30 miles per hour west to east, then they're both moving at the same speed, but they're moving at different velocities because they're moving in different directions. So why do we say that at stage 3 of the experiment, the water's accelerating, and likewise for the bucket, or at least the sides of the bucket? Well, that's because they're changing in direction, right? So acceleration is defined in terms of change of velocity, and what's happening with the bits of the water and bits of the bucket is that they're constantly changing direction, and therefore they're changing velocity. Now, it's easy to sort of get confused about acceleration because sort of informally in everyday life, we tend to talk about acceleration as corresponding to an increase in speed. So when we talk about a car accelerating, we tend to mean it's speeding up. But strictly speaking, any sort of change in velocity counts as an acceleration, whether that be a speeding up, a slowing down, or just a change in direction. Okay. So we've got absolute motion, Newton would say, in the third stage, and crucially absolute acceleration, and this is going to explain the empirical difference. The relationist is unable to explain this because the water isn't moving relative to the sides of the bottle in either the first stage or the third stage, and nor is it accelerating relative to the sides of the bottle in either the first stage or the third stage. In order for it to be accelerating relative to the sides of the bottle, its acceleration would have to be different from that of the size of the bottle. Okay, so you might say, well, we kind of set aside this point about the Earth rotating around its axis and also moving in orbit around the sun. But were we right to? So the relationists might object. They might say, well, actually, there are differences in. So if we take account of this sort of broader context, so we're not just focusing in on the water and the bucket or the bottle, then you might say, well, actually, there is a difference in relative movement in the first stage and the third stage, the relative movement of the water. The difference isn't in movement of the water relative to the bucket or to the bottle, but rather movements of the water relative to the rest of the universe. So maybe relative to the room, relative to the surface of the Earth, relative to the sun, relative to the center mass of the galaxy. So there are sort of differences in relative motion that the relationists could appeal to in order to explain the difference in the shape of the surface of the water between stage 1 and stage 3. There's no difference in the movement of the water relative to the sides of the bucket or the bottle, but there is a difference in movement of the water relative to, say, the room. Now, so Newton kind of anticipates this, and he is skeptical because he thinks that actually, specifically if one adopts his theory of what the laws of physics are, then movement relative to the room is not clearly going to explain the phenomenon in question. But what he actually wants to do is to conduct a thought experiment and say, well, look, okay, maybe you can try to give an explanation in terms of what the water's doing relative to other objects besides the bottle. But the thought experiment says, well, consider a universe in which there's only the buckets and the water. Then he thinks you could have two states, right? So you could have a state in which the surface of the water is flat and a state in which the surface of the water is concave. And he says, well, then we wouldn't have any relative movements to explain this empirical difference in terms of, because there wouldn't be anything beyond the bucket and the water for the water to be moving relative to. So what he would say is that even in such a universe where there's just the bucket and the water, we can explain the difference between the flat and the concave surface of the water in terms of the absolute acceleration that the water's undergoing when its surface is concave, and the flatness of the lack of absolute acceleration that it's undergoing when its surface is flat. So that the sort of Newtonian thought experiment. Now, of course, the relationists might just object, right? They might say, well, in a universe where there are only these two objects, maybe these two different states aren't possible. Maybe the surface of the water would always have to be flat, or maybe it would always have to be concave or something, because actually in order for there to be a difference in states, well, this would have to be explained in terms of the water's relational movement with respect to other objects. But there are no other objects in the hypothesized universe. So there's a bit of the absolutist and the relationists are at loggerheads there. Okay, so we considered the bucket argument. That's supposed to be an argument for absolutism. And we saw that, there are attempts maybe by the relationists to neutralize it. So they might say, well, look, in the third stage of the experiment, the water's moving with respect to the room, and maybe that explains why it's concave rather than flat. And then when Newton raises the hypothetical possibility of bucket and water in an otherwise empty universe, well, the relationist says, maybe there wouldn't be a difference in possible states. Maybe there couldn't be a case in which that universe, in that universe, the water was concave or something like that. So the relationist has ways of trying to neutralize the bucket argument. Are there arguments against absolutism, so sort of positive arguments against absolutism, rather than arguments that merely try to neutralize an argument for absolutism? Well, yes, there are arguments against absolutism, or if you like, for relationalism. So Leibniz is well known for having advocated some of these arguments. So Leibniz thinks that absolutism implies certain implausible possibilities. So he in discussion with a Newtonian, a defender of Newton, came up with a set of arguments that seem to he would argue make the absolutist position implausible. So he points out that if absolutism is true, then the following could have been different, right? Firstly, the position of the material universe within absolute space, right? So that will be one thing that could be different. Second, the orientation of the material universe in absolute space. And third, the speed at which the material universe is traveling through absolute space. So consider the first possibility first. So we have the material universe, all of the matter that constitutes the material universe, and maybe energy too. So the galaxies and the stars and planets and so on. Now, the idea is that firstly, if absolutism is true, then it should be possible. There's a possible world, if you like, in which all of the matter in the universe is just moved by a mile in a particular direction. That seems like a coherent possibility. It's just a matter of the matter all being shifted in absolute space. We could also have a different possible world that's exactly the same as the actual world, only all of the material universe is rotated through 90 degrees, say. We could also have a universe that differed from our own on the assumption that space is absolute, in that a uniform velocity of, say, 10 miles an hour in a particular direction is applied to every particle in the universe. This is what's known as the boost argument. So we could just have all of the matter in the universe just drifting through absolute space, maybe drifting at a different rate from the one it actually is, if it's actually drifting in the actual world. Now, Leibniz's point is that, well, if these scenarios make sense, as they seem to on absolutism, then there are going to be infinitely many of these possibilities. So we could shift the whole material universe by a mile in a particular direction, or by 1.1 miles, or by 1.11 miles. So quickly we get an infinity of possibilities. Likewise, we could boost the material universe at 10 miles an hour, 11 miles an hour, 11.1 miles an hour, 11.11 miles an hour. So again, an infinite number of boosted universes, if you like. Now, Leibniz points out that these possibilities, if they are possibilities, are going to be empirically indistinguishable from the actual world. So you wouldn't be able to tell the difference between a material universe that's like the actual material universe and one in which all matter is shifted by a mile all in the same direction. That corresponds to no empirical difference. And it turns out, at least if Newtonian mechanics is true, if Newton's physical laws are true, then you wouldn't be able to tell the difference between the actual world and a boosted world. There'd be no empirical consequences of that. So Leibniz suggests that this sort of seems ontologically extravagant, maybe a violation of something like Occam's razor, to suggest that there are infinitely many possible worlds, none of which are empirically distinguishable from one another. And so he thinks the fault is with absolutism, because absolutism is what implies that these are all possibilities, right? Because if you believe that space is like a container, then it makes sense to talk about shifting all the matter in the container by a mile in a particular direction. Whereas if the relationist hypothesis is true, then you don't have to allow that these are genuine possibilities or different possibilities, because if you shifted all the matter by the same amount in the same direction, you'd preserve all the relations between that matter, all the spatial relations between that matter, and likewise for a boost or a rotation. So the relationist can say, well, look, these aren't really different possibilities because all the relations are the same. Okay, so the kind of version of absolutism in question that's been debated by Newton and Leibniz is known as Newtonian absolutism. So, as we've suggested, this is the sort of version of absolutism we've been considering so far. The Newtonian absolutist believes in absolute space, believes in absolute velocity. Remember, velocity is defined as change in absolute space in a particular direction. And the Newtonian absolutist also believes in absolute acceleration, which is just change in absolute velocity. There is another form of absolutism available that actually looks a little bit more like a compromise between absolutism and relationalism, and so potentially avoid some of the pitfalls of that Leibniz has leveled against Newtonian absolutism. So this is Galilean absolutism, which endorses the existence of absolute acceleration, but denies absolute velocity. So how do we do that, right? So what? Firstly, why would it be good to deny absolute velocity? Well, it at least allows us to avoid the boost arguments, right? So if there are no facts about absolute velocity, if there's no such thing as absolute velocity, then we can't make sense of two worlds that differ only in one of them. All of the particles are drifting at a uniform velocity that's different from those in the first world. So it seems to do away with the boost argument, which is arguably a virtue. We'll come back to the shift argument in a moment. But it retains absolute acceleration. Now, why would that be good? So the reason that it'd be good to retain absolute acceleration is because it's acceleration that explains the difference in the two states in the bucket experiment. So according to Newton's laws, it's the fact that in the third stage of the experiment, the water is accelerating, it's moving circularly, and so accelerating. That explains why the surface is concave. Even though it's not accelerating relative to the bucket, it's accelerating absolutely, and that provides the explanation. So it seems like it might be a good thing if we could retain absolute acceleration, and so explain what happens in the bucket experiment, but deny absolute velocity, and so escape the commitment to boosted worlds. So you might think, well, but how can we have absolute acceleration without absolute velocity, since absolute acceleration, is defined ordinarily in terms of change in absolute velocity? Well, basically, we avoid that by defining absolute acceleration in a different way. So absolute acceleration is not defined in terms of change in absolute velocity, but rather in terms of an object having a curved trajectory through space-time. So here's what we mean. So we can represent space-time. So this is a simplification. We've got our y-axis corresponding to space, our x-axis corresponding to time. Obviously, this is simplified because we ordinarily think of space as three-dimensional, but we've represented it one-dimensionally. But that's not going to, for now, that's not going to make us miss anything crucial. And timing is increasing along the x-axis. So the idea is that we could trace out the path of an object through space and time, and if the object is accelerating, then its world line is going to be curved. So that's the case for object C. Curvature suggests that there's a difference in the amount of space that's being traversed over time by the object. So if we look at the line for C, object C, what we find out is that in the initial segments of C, not much space is being traversed in a given interval of time. But in the later stages, actually an increasing amount of space is being traversed in the same amount of time. So if we had our units of time be an hour, then in the sort of hours early on in object C's history, C isn't moving all that much through space, but later on, it will move much more during an hour than it would have earlier on. So that corresponds to acceleration, in this case, an increasing amount of distance being covered per temporal interval. So the Galilean absolutist wants to retain absolute acceleration and just defines that in terms of the difference between a curved trajectory through space and time versus a straight trajectory through space and time. So it sort of seems as though maybe the Galilean absolutists can kind of have the best of both worlds. So they can explain the shape of the surface of the water in the bucket experiments because they allow this absolute acceleration, but because they don't believe in absolute velocity, they can reject the existence of boosted worlds, worlds in which the whole material universe is drifting through space-time, and so they can sort of side with Leibniz and say, look, that would be ontologically extravagant, but we don't need to commit to them. However, there is a sort of drawback in it's maybe not the sort of ideal sort of view, in that while they reject absolute velocity, they don't reject absolute position, and because they don't reject absolute position, that means that the boost worlds are still the shift worlds are still a problem for them. So they still allow that objects have absolute position, and so it makes sense to talk about an alternative world in which every material object is just shifted by some distance in a particular direction, even though that would be empirically indiscernible. So Galilean absolutism is a sort of compromise. Is it the best compromise? Well, it achieves virtues of both the absolutist and the relationist position, but there are still drawbacks, like the commitment to the existence of shifted worlds. Okay, so is there anything more we can say about absolutism versus relationalism? Well, actually, interestingly, there's another argument that's worth considering for absolutism that's quite different from the bucket argument, and maybe seems a bit more metaphysical rather than empirical in character. And this is an argument due to Kant. So Kant argues for absolute space in a kind of surprising and interesting way. He appeals to the notion of what's known as an incongruent counterpart. What's an incongruent counterpart? Well, incongruent counterparts are objects or pairs of objects, like a pair of shoes. Other examples would be a pair of hands or a pair of gloves. They share all of their intrinsic properties. So they're the same shape and color and size and so on. However, so that's what makes them counterparts in his terminology. However, they're incongruent in the sense that neither object can be moved or rotated in such a way that it occupies a region of space-time that's also, or I should say, region of space that's occupied by the other. So I've got another little video to show you. Let me just pull that up. So here's a pair of shoes, and it's not going to work yet.
So the two shoes.
Sorry, let me just mute that so I can talk over it. So these are not perfect counterparts because the shoes are a little bit old, so they don't exactly have all the same intrinsic properties. It might be that one has creases that the other one doesn't, or a bit of mud that the other one doesn't. But you can imagine sort of perfect shoes that genuinely are counterparts. Now, they're mirror images of one another. So that mirror images are going to share all of their intrinsic properties, so color, shape, size, and so on. But they're incongruent in the sense that if I move, say, the right shoe out of the way, then there's no way of moving the left shoe so it will exactly occupy the region of space that was initially occupied by the right shoe. So if I'm not sure if I'm going to do that in the video, I'm about to do that in the video. So, but what you'll see is sort of if I simply moved the left shoe to the right, well, it would roughly occupy. I guess I've done it the other way around. It'd roughly occupy the same region of space that the right shoe initially occupies, but because they have a sort of different orientation, I can't get it quite right because so the right shoe curves leftward and the left shoe curves rightward. So even if I moved it across, I wouldn't have a sort of perfect overlap of the left shoe into the space that was initially occupied by the right shoe. And then if I flipped them, then it wouldn't really work either because the sole of the shoe is bigger than the top of the shoe. So there's no way I can get it so perfectly so that one precisely occupies the region of space that the other one previously occupied. Okay, so that's what makes them incongruent. Okay. Yeah, so I said that. Okay, so what Kant says, well, imagine a world containing nothing but one shoe. He says, well, that shoe would still be either a left shoe or a right shoe. That is to say, it would have an orientation, or if you like, a footedness. So we talk about right-footedness and left-footedness. These are facts about orientation. So the shoe would have an orientation, despite the fact that right shoes and left shoes are intrinsically alike. So you might say, well, okay, so they're intrinsic replicas, duplicates, they're counterparts. So like in all intrinsic respects. So how could it be that a shoe all on its own in a world with nothing else in the world would still have an orientation? Kant claims that it does. So if Kant's right, how can that be? How can it still have an orientation? Because there's nothing intrinsic to distinguish the left and the right shoe. Well, I mean, Kant says that it's got to be something relational, right? So it's not the intrinsic properties that distinguish the left and the right shoe. It's got to be something relational. But of course, if the shoe's all on its own in the universe, then how can it be something relational that makes it, say, a left shoe? So what Kant argues is that, well, yeah, there are no other material objects in the universe besides the shoe. So the relation that makes it, say, a left shoe can't be a relation to any other material objects, but rather it's got to be a relation to space itself, which is rather surprising. So he thinks it's the relation of the shoe to space itself that makes a left one or a right one if there's no other object in the universe. And so he takes this to imply that space is the sort of thing that can stand in relations. In other words, it exists. It's a thing in its own right. It's substance-like. And hence he thinks that he's demonstrated absolutism. Okay. So you might say, well, okay, maybe that's right, but couldn't the orientation be grounded not in terms of the shoe's relation? So we're imagining this. I guess there are two things you could say. So imagine this shoe all on its own in space-time. So you could say, well, look, a shoe all on its own in an otherwise empty space doesn't have an orientation. So the relationist could say that. They could say it just doesn't have an orientation. Kant would object because he'd say, well, yeah, it does have an orientation. Imagine if you added a second shoe, then it would have to either have the same orientation or a different orientation to the first shoe, which suggests that the first shoe already had an orientation. But a second line of objection that the relationist might adopt is they might say, well, okay, I grant that this left shoe has an orientation, like left-footedness, even in a world in which it's the only object. And I grant that intrinsically left shoes and right shoes are exactly alike. They're mirror images of one another. But what I want to deny is that the left-footedness, the orientation of this shoe, this lonely shoe in the world all on its own, is grounded in a relation to space. So they might say, perhaps we can ground it in a relation between the parts of the shoe itself. So the problem with this is it sort of seems like an attractive approach, but it's not quite clear how to do it. So, normally you'd say, well, the reason a left shoe, if you sort of want to look at a shoe and identify its orientation, you might sort of hold it kind of top up towards you and say, well, look, this shoe curves leftwards, so it's a right shoe, or it curves rightwards, so it's a left shoe. The curved rightness and the curved leftness, you might think, well, that has to do with the relation between its parts, so maybe we can understand what it is for the shoe to have orientation in terms of relationship between its parts. But the trouble is that actually what you've done there is you've presupposed relations between the shoe and an object external to the shoe, namely you yourself. So you've held it up with what you take to be the top facing towards you, and then you've said, well, the shoe curves left or curves right. But we can't, unless we have an external reference frame, we can't really talk about which way's right and which way's left. So actually, this sort of attempt to define the shoe's orientation in terms of relation between the shoe's own parts looks like it's going to be somewhat challenging. Okay, so I've gone on for a bit long today. That we'll leave it there. So I mean, sort of interesting arguments both ways. As ever in philosophy, I guess nothing's super definitive. So the bucket argument seems, and the incongruent counterparts argument seem to be interesting arguments for absolutism. There are things that the relationists might try to say in response, as we've seen. On the other hand, we've got arguments against absolutism in the form of the boost and the shift arguments. Those arguments maybe point to a sort of metaphysical extravagance for absolutism. maybe point the way towards relationalism as preferable, but it will only be preferable if it can account for the results of the bucket experiment and incongruent counterparts. And there are question marks over whether it can do that. Galilean absolutism looks like a sort of reasonable compromise between Newtonian absolutism and relationalism. But it's not entirely devoid of problems. So, for instance, we saw that the boost argument can be applied to Galilean absolutism just as it can be applied to Newtonian absolutism. So, there's plenty to sort of think about and discuss if this is the sort of thing you'd like to write an essay on. Okay, so that's it from me for this week, and I will speak to you again next week. Hope you have a good week, and goodbye.